We have 6 objectives in this section. First, find the derivative of a function using the constant rule. Find the derivative of a function using the power rule. Find the derivative of a function using the constant multiple rule. Find the derivative of a function using the sum and difference rule. Find the derivative of the sine function and of the cosine function. Use derivative to find rates of change. For the constant rule, the derivative of a constant function is 0. That is, if c is a real number, then differentiate the c with respect to x is equal to 0. Look at the figure below. Let's say fx equal to c, where the c is a constant. So, the slope of a horizontal line is 0. The derivative of a constant function is equal to 0. Notice that the constant rule is equivalent to saying that the slope of a horizontal line is 0. This demonstrates the relationship between slope and derivative. For the first example, let's say the function y equal to 7. So dy dx is equal to 0. And fx equal to 0. So the f right x equal to 0. And look at the last one, y equal to k pi square, where the k is constant. So y prime is equal to 0. Before proving the power rule, it is important to review the procedure for expanding a binomial. Let's say we have x plus delta x squared, and when we expand this, x plus delta x, so we have x squared plus 2x delta x plus delta x squared. And for the x plus delta x cubed, meaning that we take the expansion of the x plus delta x squared, expand with x plus delta x again. So we have x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. And we keep expanding. We will have 4th order, 5th order, 6th order, and so on. So based on the pattern, we can create a formula for the binomial expansion for a positive integer n. And this is a formula. And this binomial expansion is used in proving a special case of the power rule. If n is a rational number, then the function fx equal to x power to the n is differentiable, and differentiate x power to the n with respect to x is equal to n x power to the n minus 1. For f to be differentiable at x equal to 0, n must be a number such that x power to the n minus 1 is defined on an interval containing 0. For differentiate x with respect to x, we can use power rule because the n is equal to 1. And the meaning of this derivative is the slope of the line y equal to x is equal to 1. For the second example, For the a, we have a f(x) equal to x cubed. So the power is cubed. So we have to use power rule. And the f prime x is equal to 3x squared. For b, gs is equal to cube root of x, where this cube root of x can be written as power rule form, x power to the 1/3. And we use power rule to differentiate. So we have this answer, and we can rearrange our answer. And one more, y equal to 1 over x squared. This is a rational function, but we can convert this rational function into power rule form, which is x power to the -2. So we can use power rule to differentiate. And this is the answer, and you can rearrange your answer in this form. So now look at the step. First, you are given a function, and you rewrite into the power rule form, and you differentiate using the power rule, and you simplify your answer. For the constant multiple rule, if f is a differentiable function and c is a real number, then f is also differentiable, and differentiate the cfx with respect to x is equal to cf prime x. For this example, you can use the constant multiple rule. For example, the a, because there's a 5 in front of x cubed, so we use constant multiple rule. So where for the constant multiple rule, we can bring out the 5, the constant, out, and we just differentiate the x cubed with respect to x by using the power rule. So this step is power rule. This step is power rule. So we simplify our answer. So lastly, we have 15x squared. And same for y equal to 2 over x. First, we write it into the power rule form, which is 2x minus power to the -1, and the 2 is the constant. The 2 is the constant, so we bring out the 2, and we differentiate the x power to the -1 by using the power rule. And lastly, we simplify our answer and arrange it. Same for the rest examples. So for the constant multiple rule and the power rule can be combined into one rule. The combination rule is constant multiple rule. Differentiate the c x power to the n with respect to x equal to c n x power to the n minus 1. For the sum and different rules, the sum or difference of two differentiable functions f and g is itself differentiable. Moreover, the derivative of f plus g or f minus g is the sum or difference of the derivative of f and g. For example, differentiate the fx plus gx with respect to x. So it's equal to f prime x plus g prime x, meaning that we can straight away to differentiate the fx and the gx with respect to x. And same for different. Look at this example. We have fx equal to x cubed minus 4x plus 5. So the derivative of this function is f right x equal to 3x squared minus 4. Where we differentiate the x cubed using the power rule, and differentiate the negative 4x using the constant multiple rule. And we differentiate the 5, we use constant rule. And look at the C. The original function is the rational function, but we can convert this rational function into the sum and different form. And we use sum and different rule to get the derivative of the function. And for the 3x, we use constant multiple rule. And for the negative 1, we use constant rule. And for the 1 over x, we use power rule. Make sure you convert this into the power rule form. The derivative of sine and cosine function. Differentiate the sine x with respect to x is equal to cos x. But differentiate the cos x with respect to x is equal to negative sine x. Look at this example. For a, y equal to 2 sine x. To differentiate the a, we use constant multiple rule, where the 2 is constant, and the sine x is the trigo function. So the y prime is equal to 2 cos x. Look at the d. We have cos x minus pi over 3 sine x. Look at the main function. The main function is in the sum and different form. So we use sum and different rule. And we can straight away to differentiate. So we differentiate the cos x, we have negative sine x. And we differentiate negative pi over 3 sine x, we use constant multiple rule. So the constant will remain negative pi over 3, and we differentiate the sine x, so we have cos x. You have seen how the derivative is used to determine slope. The derivative can also be used to determine the rate of change of one variable with respect to another. Applications involving rate of change occur in a wide variety of fields. A few examples are population, growth rate, production rate, water flow rate, velocity, and acceleration. A common use for rate of change is to describe the motion of an object moving in a straight line. In such problem, it is customary to use either a horizontal or a vertical line with a designated origin to represent the line of motion. On such lines, movement to the right or outward is considered to be in the positive direction, and movement to the left or downward is considered to be in the negative direction. The function s that gives the position is a relative to the origin of an object as a function of time t. Is called a position function. If over a period of time delta t the object changes its position by the amount delta s equal to s into t plus delta t minus st. Then, by the familiar formula, rate is equal to distance over time. The average velocity is change in distance over change in time, and also equal to delta s over delta t is average velocity. A billiard ball is dropped from a height of 100 feet. The ball's height s at time t is the position function, where s is measured in feet and t is measured in seconds. Find the average velocity over each of the following time intervals. For the A is from 1 to 2, for B is from 1 to 1.5, and C is from 1 to 1.1. So for the A, the interval is from 1 to 2. The object falls from a height of s1. We substitute the 1 into the position function, and we have 84 feet to a height. And when t equal to 2, we substitute into the position function, we have 36 feet. So to calculate the average velocity, the formula is delta s over delta t. So it's equal to 36 minus 84 over 2 minus 1. So we have negative 48 feet per second. The negative is indicating the direction. And same for the B, from 1 to 1.5. So we substitute the t 1.5 into the position function, and we have 64 feet. And use the average velocity formula. We have 64 minus 84 over 1.5 minus 1. And the answer is negative 40 feet per second. We use the same method to solve the C. And again, I repeat, the average velocities are negative, indicating that the object is moving downward. In general, if s equal to st is the t function, is the position function, for an object moving along a straight line, the velocity of the object at time t is vt equal to limit the s t plus delta t minus st over delta t, where the delta t approaches 0 is equal to s prime t. In other words, the velocity function is the derivative of the position function. Velocity can be negative, 0, or positive. The speed of an object is the absolute value of its velocity. Speed cannot be negative. The position of a free-falling object, neglecting air resistance under the influence of gravity, can be represented by the equation, where s0 is the initial height of the object, v0 is the initial velocity, and g is the acceleration due to gravity. And there are two values for gravity. Negative 32 feet per second or negative 9.8 meters per second. Look at this example. At time t equal to 0, meaning that at initial time, a diver jumps from a platform diving board that is 32 feet above the water. So look at the figure here. The height from the water surface is 32 feet. Because the initial velocity of the diver is 16 feet per second, the position of the diver is given by this function, where s is measured in feet and t is measured in seconds. When does the diver hit the water? And what is the diver's velocity at impact? Look at the A part. To find the time t when the diver hits the water, let s equal to 0 and solve for t. So we let the position function equal to 0 because when the diver hit the water, meaning that there's no distance from the platform. The distance is equal to 0. So that is why we let equal to 0. And calculate the t. And we have a two value of t, negative 1 and 2. And because of the t is impossible negative value, so t is equal to 2 seconds. And to calculate the velocity, we differentiate the position function. So we have negative 32t plus 16. And we substitute the t equal to 2 into the velocity function. And we have velocity is negative 48 feet per second.